first I want to thank Nicola and the other organizers for inviting me. It's a great pleasure and honor to be here in Moscow, where lots and lots of great mathematics came from, which we like and enjoy. And the work that I'll be describing is joint work. Joint work with Yair Solomon, who's my former student, now postdoc at Stony Brook. And we are interested in the following problem, which is a classical problem called the Danzer problem. So this is a problem in geometric combinatorics, you might say. And so I think it's of interest to many people in this audience. So the Danzer question is the following. So start with the definition. So a subset of Euclidean space, Y, is called the Danzer set, if it intersects every convex subset of volume 1. So any cube, any long box, any ellipsoid of volume 1, not necessarily centrally symmetric. Okay, so and the question, the main question, question of Danzer from the 60s. It's still open. Does there exist a Danzer set Y such that the number of points in the intersection of Y with the ball around the origin of radius t grows like the volume. This is still open. So if you're thinking about lattices, for example, lattices will not do the job because you could fit the lattice. You can fit an arbitrarily large convex subset between the rows of your lattice, which will not intersect the lattice, so it has can be made to have volume bigger than 1. So lattices will not work. Nobody knows whether such sets exist or not. And I would say that people that we've asked seem to believe that these sets do not exist, but there's no proof. Okay, so let me formulate some variants of this question, which have been formulated by other people. So, variants. There's a question of Bosher-Nitzan. Bosher-Nitzan is making stronger assumptions on this rather than this requirement, and he's asking whether such sets with these stronger assumptions do exist. So a set is called Delaunay, named after the famous, Russian mathematician Boris Delaunay. And the set is a discrete subset of the plane or of Euclidean space. Is called Delaunay if it's uniformly discrete in this sense. So the distance between any 2 points is bounded above by a fixed lower bound, and it's almost dense, which means every ball, sufficiently large ball, contains an element of the set. I didn't write down the full definition of Delaunay set. It has 2 conditions, but one of them is implied by this Danzer condition. Okay, so this is Boshanitsyn's variant, and this is the way that we heard the question, and then there's a variant of Gowers. So Gowers is asking whether you can find a Danzer set which has the following additional property, which again is stronger than this growth property, and that's that in every convex subset of volume 1, the number of points is also bounded from above. So it's bounded from above and from below by, it's bounded from below by 1 by the Danzer condition. It's bounded from above by this assumption, and Gowers wants to know if such sets exist. So these are all open questions, and then finally let me formulate the finitary variant. So does there exist? Such that for every epsilon, there's a set Y in the unit cube such that Y intersects every convex subset of the unit cube and the number of points in Y is bigger than C over epsilon. This is the variant that's usually studied in the combinatorics literature, and this is sometimes called the Danzer-Rogers problem, as far as I sorry. Thank you. Okay, are there any questions about the questions that I've put down? So these questions, like I said, are still open. They seem to be quite difficult, and so we want to make some kind of partial progress. So what does partial progress actually mean here? So to explain what partial progress might mean, let me tell you about some results of Bama and Woods. So these are the theorem from 1971, and it has, this is a paper from 1971, and in fact there are two results in this paper. The first result says that a finite union of translated lattices is not a Danzer set. And the second result says that there exists Y, which is a Danzer set, and the number of points involved radius t behaves like t to the d times log t to the d minus 1. Okay, so there are two theorems here. One is ruling out a potential source of examples of Danzer sets with the correct density. And the other is exhibiting Danzer sets with a slightly bigger density than with us.
So there's no samples, but we can prove existence of such.
Yeah, so the original question was whether there exist examples with this growth, without this logarithmic term. Okay? O of t to the d. And Baba and Woods are saying if you allow a little bit extra, some more points, then you can prove existence.
Is it a simple existence proof, or does it concretely appear?
It's a concrete construction. In fact, it's a union of countably many translated lattices suitably chosen, growing it at the correct rate, and it gives an example. Did I answer your question?
Partial answer to those
So I'm saying that statement 1 is a partial answer in the sense that it's giving evidence to a negative question to these questions, to a negative answer to these questions. It's saying that there's a negative answer within a certain type of sets, type of examples you cannot find in construction. And the part 2 is exhibiting Danzer sets which do not have the correct density as asked in the question, but slightly bigger density. Okay? So what do we prove? So we have several results, and they all have the same flavor. So the first result is that the finite union of kind project sets it's not a Danzer set. I'll explain what pattern project sets are for spend a few minutes explaining that. Another theorem is that the vertex set with substitution tiling, the primitive substitution tiling, not a Danzer set. I'll explain what a substitution tiling is. And the third result is that there exists set Y, which is Danzer, and the growth here. The growth is t to the d times log t. So we shave a few powers of log in this result.
What's D in this?
D is always a dimension of the ambient space. We're looking for a Danzer subset of R to the D. D is the dimension of Euclidean space, and it's a parameter for the problem. So in the case that D equals 2, the Bamba Woods bound and outer bound are the same, but in dimensions bigger than 2, we're getting an improvement. Okay, so I need to tell you what kind of project sets are and what are primitive substitution tilings. So the best way to explain that is to start with a picture. So this is a famous set which is called the Penrose set. You're seeing it up here. How do I use the beamer? So this is a tiling of the plane, and it's called the Penrose tiling. It's tiling made of two kinds of tiles, two triangles with two shapes, two sizes. And the vertices of this tiling are some discrete set. In fact, it's a uniformly discrete set. It's a Delaunay set. And it just so happens it's a very famous construction in the theory of quasicrystals. And it just so happens that this particular construction is an example both of a cutting project set and of a substitution tiling. So, in other words, there's some. Let me just give you kind of a pictorial description of what people discuss when they talk about the notion of quasicrystal. So there's a theory of quasicrystals, which is not a very well agreed upon theory. Many people discuss quasicrystals, and there are quasicrystals in the chemical literature, and in the biological literature, and in the physical literature, different people, and in the mathematical literature. Different people mean different things. But what's going on is that you're looking for subsets, discrete subsets of Euclidean space, which are not periodic, but nevertheless they share some of the structures of periodic sets. And so, kind of very, very vaguely speaking, there's a whole range of constructions which one might call quasicrystals. And inside this set, there's a nice class of sets called cutting project sets. And there's another type of construction coming from substitution systems, substitution tilings. And Penrose is an example. The Penrose tiling was constructed in the 70s. It's a very, very famous example in this theory, and it belongs to both families. So it's kind of a prototypical quasicrystal. So what I will do for the next few minutes is I'll explain the definition of a cutting project set, and I'll explain the definition of a substitution tiling. So let's start with cutting project. So in order to construct a cutting project set, you have to choose a lattice. So you choose two numbers, d and n, two parameters, d and n. D is the dimension of the space in which you want your set to live, and n is the dimension of some auxiliary bigger space. And you choose the lattice L in Rn. And you define two orthogonal projections, pi 1. So let's denote by x1 through xn of vector x in Rn. So then pi 1 of x will be x1 through xd, and pi 2 of x will be xd plus 1 xn. take a bounded set W in Rn minus D, and the set that we define is that we define as a projection onto D dimensions of the intersection of the lattice with the preimage of this bounded set W. So let me draw a picture so that you get a better feeling for what this is. So I'm taking a two-dimensional situation. So L is going to be a lattice in two-dimensional space. W is a bounded subset. So I'm just taking an interval in the real line, and the lattice maybe looks like that. So I'm drawing L for you. Okay? And we're looking at the lattice points which lie in the preimage of W. So the preimage of W is this under pi 2. Pi 2 is a projection mapping onto the y-axis in this picture, and pi 1 is the projection mapping onto the x-axis in this picture. So the preimage of W under pi 2 is this big cylinder, and we're looking at the lattice points which are inside this cylinder, and we project them down. So in other words, we project this point, and we get a point here, project this point, we get a point here. Okay? So this is the way the construction works. And you get a certain discrete subset of, aperiodic discrete subset of R to the D. So this is a very well-known construction in this theory. And now let me tell you about substitution tiling.
This is a formal definition of consequent function, right?
Yeah. So in the, I should say that in this construction, y depends on the lattice L and on the window. W is called the window. So y depends on two parameters here, which is one of them is the lattice that I chose, and the other is the window. So I'm fixing once. I fix once and for all these dimensions and these projection maps, and then I'm free to vary the lattice L and the window W, and that's giving me some collection of sets, which are the parameter spaces, the parameters, you might say, for the tangent project sets arising from these fixed dimensions in it. Okay, what is, any more questions about tangent project? Okay, so what is a substitution tiling? So suppose you have T1 up to TR polyhedrons, and you have some number lambda less than 1, and you have a way of presenting each of these polyhedrons as a union of contracted versions of the polyhedron. So, and so Pi will be the union of lambda for phi ij okay. Where Phi ij is a map of the form lambda x plus y ij. So each Phi ij is a contraction and a translation, and this is a disjoint up to boundary union. So let me just write it here. So put a dot inside, and this is disjoint union, except intersections of boundary. So what are we doing? We're representing each polyhedron Ti as a finite union of, so J goes from 1 to some parameter Si, some finite number of translates of the contracted versions of the original tiles, of the original polyhedron. So let me just draw you one picture which corresponds to this construction, and you just see it. So in this construction, there are two tiles. They're both triangles. One of them is an isosceles triangle that has a very acute apex angle, and the other is another isosceles triangle which has an obtuse apex angle. And there's so let's call this guy A and this guy B. And inside here, there's a little copy, I'll call it little b, of this triangle rotated, and another little copy, let's call it little a, of this triangle contracted and rotated. And here also, you can do something like that. It's not a very good drawing, but here we have a little copy of B, a little copy of A, and another little copy of B. My drawing is not very good, but this is called the substitution rule. So let's look at the slide here. So let me find a nice location. So look at the triangle with one vertex here, one vertex here, and one vertex here. And it's got another small triangle, three small triangles inside it, which exactly fit this pattern. And similarly, if you look at a triangle with one vertex here, one vertex here, one vertex here, it's got two triangles inside it which exactly fit this pattern. And so the way to get these tiling pictures is you start with one of these tiles, then you subdivide it according to this rule, then you inflate the picture by a factor 1 over lambda, and so you get a finite union of these tiles, and then you subdivide them again and inflate again, subdivide and inflate, subdivide and inflate, and you get bigger and bigger patches, finite patches, which are covered by tiles, and then there's a compactness argument that shows you that you can extract from this the tiling of the entire Euclidean space. And such a tiling is called a substitution tiling, and the set that we're interested in is the vertex set for such a substitution tiling. Okay, so that's the definition of all the terms which appeared in the theorem. And So now let me give you tell you a little bit about how the theorems get proved. So let me remind you, as you erase the theorems, let me remind you what the theorems were. So the first theorem was that using this construction of a cut and project set, we're not going to be able to construct a Danzer set. The second theorem was that using this construction of a substitution tiling, we're also not going to be able to construct a Danzer set. And the third theorem was that there do exist Danzer sets which have this order of growth. So the most difficult of these three results is the result that says that you cannot construct Danzer sets using cut and project constructions. So I'll spend a few minutes on this result. Let me just kind of indicate very briefly how you prove the other two results, and then I'll focus on that result. So let me just say, by looking at the picture without writing anything down, why it is that you cannot form a Danzer set from a substitution picture. Okay? So let's look at one of these substitution pictures. And what I'm claiming is that in this picture there's a hierarchy. So every tile here belongs to a bigger tile of one of these two shapes, which in turn belongs to a bigger tile of one of these two shapes, which in turn belongs to a bigger tile. So, for example, suppose we start maybe with this triangle here. Okay? This triangle is part of this triangle, slightly bigger. This triangle, what is it part of? It's a part of this triangle. Which is 2 times the size. This triangle is a part of, where is it? Which is that much bigger, and so on. This big piece is a part of what? It's got to be a part of something. Maybe there's it's a big part of this piece. And so on, right? That just comes from inverting the construction. So the construction, you sort of prove by induction that all of the pictures, the finitary pictures that you see, have this hierarchical structure, which is called an inflation rule. So now suppose we have an inflation rule, and we're trying to find a convex set which intersects no vertices of the picture. So that I'll just draw you a picture. Somewhere in this picture, there's a huge triangle, and this huge triangle is made up of lots of tiny little pieces, right? But on this huge triangle, there's a long, long, long straight line, and along this straight line, there are little vertices, but the vertices are either on the line or a positive distance away, because all the pieces have a lower bound on the distance between their vertices. So that means that you can squeeze in a long ellipsoid of area 1 close to one of these lines. Okay, so it's just a completely simple geometrical proof. Let me, if I have time, I'll say a few words about the improvement to the logarithmic term, and let me spend a few moments explaining how we prove the result about cut and project sets, which is, I think, is the most interesting, and it makes it clear that this seems to be a question in geometry, but it's actually a question in dynamical systems. So let me explain why one can view this as a question in dynamical systems. let's we define a Lie group G. Let me call it G0. So G0 is the group so it's the affine group of Euclidean space RD. The 0 means orientation preserving. The 1 means volume preserving. So these are volume preserving volume and orientation preserving maps. Affine maps of RD. Okay, so the standard group theoretic notation for this group is SLDR semi-direct RD. The RD part is the group of translations, and the SLD part is the linear parts of the affine maps. So any affine map can be presented as the union, as the composition of a translation and a linear transformation, and that's the group that we are interested in. And now suppose we have a Danzer set. So if we have a Danzer set, we can apply the affine group to it, and we have the following interesting property. Why is Danzer? There exists a number T0 such that Y is Danzer if and only if for every G in this group T0, if you apply to Y, if you apply this element G to the set Y, you intersect the ball of radius T0 around the origin in this space. So in other words, what this is saying is a set is Danzer is equivalent to saying that no matter how you move it around by the affine group, you can't make it disjoint from a certain ball around the origin. This is exactly the ball of radius of volume 1. Okay, why is that? Well, if you are able, if this intersection was empty, then apply the inverse of G, and you're getting that Y does not intersect the image of this ball under this pre-image, the image of this ball, the pre-image of this ball under G, which is a convex set of volume 1, because elements of G preserve, they map balls to ellipsoid, which are still convex. And conversely, I mean, if you were, okay, you can figure it out. The converse uses the fact that in this kind of a problem, there's really no difference between discussing ellipsoids and discussing any other convex body, because there's a John's theorem that says that all convex bodies up to some uniform bound have the same shape. Okay, so. Let me leave the rest of the argument to you as an exercise. So, corollary here. Suppose we want to prove. Sorry. Let me first. Let me introduce an analytical system, which is kind of a surprising analytical system the first time you see it. So let me denote by calligraphic C the set of all closed subsets of R2B. So this is, right now this is just the set, but in fact this is a compact topological space under a certain topology called the Chaboty topology. So this is compact. topology called a Chabot. Topology, what is the Chabot topology? It's very similar to the Hausdorff metric on compact sets. So the Hausdorff metric is a metric on compact sets that says the two compact sets are epsilon closed if if each is in an epsilon neighborhood of the other. Here we cannot use the Hausdorff topology because RD is not a compact space itself. We use a variant called the Chabot topology, and it says that the distance between two sets x1 and x2 are the infimum of the epsilons such that xi belongs to a xi intersect the ball of radius 1 over epsilon, a big ball around the origin, is contained in an epsilon neighborhood of xj for j and I for both choices of I and j. This is a metric on the space of all closed subsets, and it's a nice metric that makes this into a compact topological space. And clearly the affine group is acting, because the affine group is acting on RD, so it's moving compact sets around. And so, as a corollary, in order to show, or let me put it this way, Weiss and RD, then the following are equivalent. There's no scaling, there's no positive number C, such that Cy is Danzer, and the orbit of Y under G0 G0 Y closure, which is the closure of the orbit of Y, in this dynamical system contains the empty set. So let me formulate a conjecture which implies some of the variants of these Danzer questions. So here's my conjecture. Every orbit closure for the dynamical system G0, this affine group, acting on this space of closed subsets of RD, contains one of, at least one of, two fixed points the empty set and the entire set. In this dynamical system, where the affine group is moving around closed sets, there are two obvious fixed points. One is the empty set. The empty set is mapped to itself by any element. The other is the total space RD, and there are no other fixed points, right? Because if a set is a fixed point, then it would have, and it has one element which is in it, and one element in its complement, you can find a translation which moves that set away from itself. So this is a very, very strong statement about this dynamics. It says that any invariant closed set in this dynamics contains one of these two fixed points. And if true, this would give us lots of information about the Danzer question using this corollary. Because if this is true, then any set Y, either in its closure contains the empty set, which means by this corollary that it's not a Danzer set, or it contains the full set, which means that it's at least large, very large ellipsoids. Somewhere it's very, very dense, because that's what it means to have full space in the orbit closure. For example, this conjecture would imply the Gowers variant of the Danzer question. It would imply that there is no set satisfying Gowers variant. So let me make that down. The conjecture implies no set gives satisfies. So the answer to Gowers question is okay. I have 2 minutes, right? Or 3. Okay, so how do we use this dynamical idea to understand the cutting project sets? So unfortunately, we don't have at all good understanding for this dynamical system. We don't really understand how the affine group is acting on the space of all closed subsets. But we do understand how the affine group acts on lattices. It's kind of a very, very classical topic, and there's a theorem of Ratner that describes exactly what orbit closures for lattices look like. So what we're going to do is we're going to let G0, so to prove the result about cutting project set, let G0 act on the space of shifted lattices in Rn. N is the big dimension here. It's acting on the first d coordinates, as it usually does, but we're thinking of the way that it's acting on the lattices in total space of the construction. And Ratner's theorem says so I don't want to say much about Ratner's theorem. It's a very big topic, but those of you who know Ratner's theorem, what it's going to tell us is that the orbit closure of L, where L is a shifted lattice, equals the orbit under an algebraic group H and this is an algebraic subgroup of the group of affine maps of Rn, of the bigger space Rn. So any orbit closure for this action on lattices gives an orbit of a bigger group. And then with further work, one can classify these orbit closures and prove that there's no compact orbit in this action. So using Ratner plus classification theory of algebraic groups, we prove that for any shifted lattice L, so no shifted lattice L, has a compact orbit closure under this group G0 in the space of shifted lattices. And can I take one more minute just to give you the punchline? And what is that? Here's the punchline. The punchline is that when you apply this affine group and you consider the picture that I had before with this construction of cut and project sets, you can find elements of the affine group which make the lattice up here very, very degenerate, very, very far from a compact subset in space of lattices. And what this means is that it now begins to look like this. It's sets of points which are very close to each other in some hyperplanes, and the hyperplanes are very far away from each other. So if the window is lying over here, then there are patches which do not intersect this pre-image of the window at all. And then when you project down, you get big, big open spaces in the cut and project set, which is what we mean by that. Thank you very much.
Any questions?
I have a question. Has anybody tried to apply a probabilistic approach? Say you can consider a certain number of points uniformly distributed in a ball centered at the origin and very large radius.
Right.
Probably
So,
sort of a probabilistic
if you use kind of, yeah, people have tried. If you use a kind of a standard probabilistic models for discrete sets, like Poisson process and so on, then there's always, even if it's a rare event, there's always a probability of getting a big empty patch, which is bad for the Danzer problem. If you take a probabilistic model that chooses a big discrete superset, like many probabilistic models start with the lattice, and then erase elements of the lattice with some probability. Well, if that construction were to give you a Danzer set, then even the original lattice would have been a Danzer set, which it's not. So there is no obvious candidate for a probabilistic model. And so that's all I can say.
Any other questions?
Well, this Penrose set comes to a Danzer set.
How close to?
How close? I mean, which boundary you get from the Penrose set? Try.
I didn't understand the question. I mean, the Penrose set, because it's both a substitution tiling and coming from cut and project, then actually in some sense we're giving two different proofs that it's not a Danzer set.
Okay, but your boundary, which was T to the D log T.
Oh, I see.
That's from a.
So this set is uniformly discrete, which means its growth order is T to the D. In this case, T squared. So you cannot, if you wanted to, it might be possible to take the Penrose set and add carefully chosen points and get a Danzer set and maybe improve our upper bound, but that's why. Yeah.
Would you think about some subsets of all the convex sets of volume 1 for which Danzer characteristics need to, for example, as far as I understand, the ellipsoids are sufficient or not?
So yeah, the conjecture about ellipsoids is it's equivalent to the conjecture about all convex sets.
But they estimate.
Yeah, absolutely. So by John's theorem, whenever you want to,
No, the subsets which are complete, if they get proof for them, then you prove the other.
yeah, right. So any let's put it this way: any family of convex sets which are invariant under all affine transformations.
I see, but maybe some different
Yeah.
interpretations.
So I think if you use plane, axis parallel rectangles, then Danzer sets of the correct densities do exist for axis parallel rectangles.
They're not complete. I'm asking about the complete sets.
What is the definition of
If
complete?
complete, if you prove for them, they are sparse in the maybe in the whole set of the complete sets, but they are sufficient to prove.
Yeah.
So
So the
the
ellipsoids are such an example, and every, like I said, every subset of the set of convex sets which is invariant of the final group.
Okay. Let us thank our